I think we're live. So let's go back here. So now we have, what, 15, 16, 17 people here? So let's change. So we have a binomial distribution for a random sample of 17. Is this really a random sample? What kind of sample is it? You guys know this. Start with a C, O, N. What kind of sample did I just take? It's not a random sample. There's nothing random about you guys.
Convenience.
Convenience, yes, Michelle. Melissa, sorry. And I had the M right, and a couple other letters. Two other letters, okay. Apply. Oh, that shifted it a little. Did you guys see that shift? That was cute. All right, so looking at this, I would estimate the mean of this distribution to be about, what do you think? About what? Can you tell by looking at the distribution about what the mean is? 11, that's the highest stack, right? And Michelle pointed out that the, yes, I was referring to her this time, the other Michelle, that the mean of a binomial distribution is found by multiplying n times p. What's the expected value of a binomial distribution? NP, yes, it is also NP. Expected value and the mean are the same. So what is 0.62, 62% of 17?
10.54.
So about 10 and a half?
Yeah.
We go to 1 decimal point. That's the round off rule, right? We go one more than the data, and the data is whole number of people. So we are we're going off with a BMCC claim. So that's not a Hi, Lewis. Claim 62% female students. And we have a sample of n equals 17. We're just going to stick with that 17 for now since we started calculating. What's the standard deviation? How do I find that? So mu was NP. How do we get sigma?
The square root of n times p times q.
N times p times q in the square root, correct. All right, so if you guys could whip out that calculation for me. Let's see, what's that? 17 times 0.62 times, what's that, 0.38? Did I get that right? What do you think, Jason? 2.0 is the standard deviation. Okay. Let's see, what else can we do? Well, we actually have females in this room, so we can actually count to see what we have here to compare it to 62. So 1, 2, 4, 5, 6, 7, 8, 9, 10. Can someone verify that for me? 10 people. Okay. So we, in this particular not so random sample, have x equals 10 females. Now, when you take a sample and you use that sample to make a proportion, in which case we're going to use that to find the proportion of females in this sample how do I actually calculate the proportion of females here? What do I do with arithmetic? Yeah, 10 divided by 17. Okay, so that's x over n. And for us, that is 10 over, whoa, crazy pen, sorry. 10 over 17. And to, let's see, can I have 3 decimal places on that? 0.667. Agreement? Everybody? 0.588.
Yeah.
10 divided by 17.
15.
Okay, so it's 2 decimal places. It's 0.588. So like 58.8%ish. Okay, so 0.588. Okay. This is what we call P with a little hat on top. P hat is about 58.8%. We're a little bit under what the claim is. Oh, let's see, this is students. I'm not taking a class this morning. I was last, so I guess that counts. So Louis, you get to count instead of me. Okay, so we still have 17. It's still 10 out of 17. It's 58%. Okay, so did we nail the BMCC claim in this class? Oh, we're pretty close. Okay, so can we like say how close that is? So we are under. Right? So is that so we're less than the mean, right? 10 versus 10.5. Pretty darn close though, right?
Yeah.
Yeah. Now, if I were going to round 10.5, I would say it'd be 11, not 10. That's okay. So this is probably not unusually low. Can we check that? Okay. How would we check that? So let's see. If something's unusually low, do we do a PDF calculation or a cumulative calculation for unusual? PDF or cumulative? It's cumulative. Unusual events, you have to look at a left tail or a right tail. Are we doing a left tail or a right tail here? Left, because why? Because it's lower than the mean. Yeah, I have a percent that's lower than the given percent, which means I have a proportion that's less than, or I have a number of females less than the mean of what females should be theoretically. All right, so we're going to calculate a left tail. So what calculation are we going to do? So. No, that's a right tail is 1 minus. Yeah, left tail is what it does naturally. So is this x equals 10 females, an unusually low number of females? And we can pretty much see it's not, because it's pretty darn close to the mean. So let's calculate it anyway. An unusually low number of females. So everyone, let's do this calculation and see if we all get a similar number. So I want to know, what is the probability that x is less than or equal to 10? And less than or equal to is what the binomial distribution, the CDF, does. Let's see, what's n here? That would be x. X is 10. 70. We're going to go with 17. We're going to ignore me now because I am not a student at the moment. So we're going to go with 17. What is the probability of a success according to BMCC? 0.62. And we are letting x be 10. And what do we get on that to 3 decimal places? So about 48.4%. And a number of females would be unusual if that probability was in what range? Less than 5%. Then we would say it is unusual. And that's much greater than 5%. So this is typical if the BMCC percentage is right. And I have a random sample. Now this sample isn't random, it's a convenience sample. There could be enough randomness involved in how you got here. That'd be okay, but maybe not. So this x equals 10 females is not at all unusual. Would you say it's very likely to have 10 out of 17 randomly chosen students be female? Yeah. So then it gets to matter, like, well, what do you believe highly likely is? And we don't have a definition of that. It's just whatever somebody thinks, right? So I usually think highly likely is like in the, I don't know, above 75%. Some people say, hey, above 50% is highly likely enough for me. So that's just a matter of opinion. But the unusually low events, we do have a rule about that, right? And that's if the resulting probability of either of the tail we're looking at is less than 5%, it's unusual. And this is usual. Some people might say 48% is pretty darn likely. Others might say it's not likely enough, but it's definitely not unusual. Okay, so that's just a review of stuff we did before. So we're going to do something new. Check out the distribution again. That kind of bell-shaped? It's pretty bell-shaped. So what I'm going to do is I'm going to graph a normal distribution on top of this. To graph a normal distribution, you need 2 bits of information. Anybody know what they are? What 2 things you need to know to graph the right normal bell? The mean and the standard deviation, right. Do we have a mean and a standard deviation here? Yeah, we got those. So what we're going to do is we're going to try to approximate a normal distribution with, we're going to try to approximate this binomial distribution with a normal curve. Now, couple problems with that. This thing is slightly skewed. Which side has a longer tail? Left. Binomial distributions are never skewed. So it's bell-shaped, but it's not unskewed. It's not balanced. There's a little bit of skew to the left because that's where the tail is. And the other thing, a normal distribution is what we call a continuous distribution. You can have 10.5 and 10.1. But this is a discrete distribution. I can have 10 or 11, but nothing in between. Because we're talking about the number of people. So, but sometimes it's helpful to use a normal and a binomial together. And I'll show you a reason why today. So let's see. What, again, is our mean and standard deviation? 10.5 and 2.0. If we go to the nearest 10th, maybe I want to go a little finer than that. What would they be to the nearest 100th? Somebody help me check that. If I had put one more decimal place for the mean, or was that exactly what it was? It's 5.4. Okay. So maybe we go 10.54. It might not make a difference in the graph. We'll see. And then if I take the standard deviation to 2 places instead of 1, it's still 2.00. Okay. Cool. All right. Let's do it. So some programs allow you to draw these curves. We don't really need to here. I just want to show you that it's possible. And we are going to actually use this result, although we don't usually need to draw the picture. GeoGebra has a really nice feature for drawing normals, and it just asked me for what the mean is, and we're going with 10.54, is that right? And standard deviation is 2.00, I'm just going to call it 2, and then it's going to let my variable be x, and it's going to draw the curve. But that's not bad, huh? It kind of goes through almost the center of each stack. Good. That is pretty darn good. So what I've just done is a normal approximation of a binomial. And there are times when you can get away with that, and there are times that you can't. So let's write down the rule for when we can get away with it. And then I'll show you why the hell we do it. So we're looking at a normal normal approximation to a binomial distribution, and we're going to need that to generate z-scores for the situation we're going to try in a minute. And you can get away with that if n times p, which is your mean, is greater than or equal to 5, and n times q is also greater than or equal to 5. Check my notes that I'm not lying. Somewhere. There's a cute little table I'll show you about this. Aha, there it is. So I was kind of curious, like which combinations of N and P and Q make this work. So I did a little grid with N, P, and Q, and I highlighted all the letters, all the results. For now, I'm skipping a lot. Like I didn't do every possible P and Q because there's infinitely many decimals in there. But I did numbers like 0.05, 0.1, 0.15, 0.2. And I'll show you this graph. But do you see a pattern to my shading? For those of you online, I'll show this graph on the computer. It's kind of cool, isn't it? It's colorful, and it's got a nice double shape. Weird. So is that true for our case? So let me see. What's our NP for this one? It was 10.5, right? So NQ would be our 17 times Q, and Q is 1 minus 0.62, which is 0.38. What's 0.38 times 17? Which is greater than 5. So we are safe, and the picture looks good. Okay. Let's see where the hell did my file go. So we satisfy the requirement for when we can approximate a binomial with a normal. 243 normal binomial. Nothing else. Normal binomial. That is half of the picture. Here's the graph. Right there. Do a combination. Oh, there it is. Okay. So here's my grid. So what I have going down the side are my n's, sample of size 1. That's kind of small, right? Pretty rare we're going to use a sample of size 1. In fact, we almost never do. 5, we push that limit on occasion, but usually your sample size is going to be bigger than 5. If you're using the central limit theorem, which we will use a little bit, what should n be for that? 30 or bigger. Usually bigger than 30 is what we say. So really for the central limit theorem, we're going to be way down past this row right there. And in the top, I have P going from 0.05 and then increasing by 5% each time. So 5%, 10, 15, 20, 25, 30, 35, 40, 45, 50. Notice the peak happens at 50. Balance, right? Because that's where P and Q are equal. And then we get a mirror image on the other side. Kind of. So I just wanted to see for fun. So I have this table, so I have kind of a quick check. If somebody says their sample size is 30, then I can see in what range of P's and Q's will work. And so scrolling up here, I can see that if you have a sample size of 30, as long as the percent P is from 20% up to 80%, you're good. You can get away with this normal approximation. Okay, so who cares? Why do we want to do that? Well, I mentioned earlier about a big thing about the central limit theorem. It allows us to take a bunch of small samples and get information about the whole population, which is often important. And so we're doing more work in that way. So how can we, this is the big question, how can we use samples to predict things about a population? And then a question that goes with that is, what kinds of things do we want to predict? So things we might predict is a portion of the population that is female. So here's one example. A proportion. So why would we care what proportion of the population is female? Anybody have any instances? weird picking on females. All right, so I'm going to pick on females a little bit. In the tech industry, the percent of women working in high-tech jobs is rather low. It's so low, in fact, that there's this weird thing some tech companies do. They consider it a huge milestone if they have more women than they do guys named Dave. Which is kind of sad. I mean, like, why aren't women going into high-tech fields? Why aren't there a lot more women programmers, web designers, things like that? Is like programming too nerdy, geeky guys that hang around in their shorts eating pizza and playing video games kind of thing, and it's just not appealing to women? Maybe there's something else. I don't know. But this is a big deal in the tech world. A lot of companies are saying, how can we get more women out there? Right? Because half the people in the world are female, roughly, and they use tech stuff. Maybe we need their input to make tech stuff better. Other thing is, what? I had some other ideas, and I just spaced it out afterward. The guy named Dave thing is true. That's a measure a lot of companies use, that they're improving. Yeah, I know, right? Why Dave? I don't know, but that's a measure they use out there. These aren't helping me out at all here. I did notice the other day that the proportion of women on the Timber soccer team was 0. What's up with that? It's a little gender discrimination. Okay, that was a stupid one. You guys aren't going to help me out with any reasons we might want to. Okay. Proportion of females. How about proportion of males? Let's pick on men then. Fine.
Part of men.
Yeah.
Advertising is really to figure out who they should
Target.
sell.
Yeah, I just heard some things that when Obama was running for the presidency, they made a big push using online media to target women and minorities, African American, Hispanic American. And so they wanted to know what proportion was out there and how they're going to target it. So they were doing all kinds of statistics with that. Okay, so we're not making much progress there. Let's move on to something else. Other things we might want to calculate. Now, there's all other kinds of proportions we might look at. I had a problem on the test the other day, proportion of green-eyed babies. I don't know why we'd be interested in that, but we were at that moment. But proportions are one big thing. What percent of the population fits a certain characteristic? Other kinds of things we might want to know is what's the mean of some measurement? Like, example, mean height of a population. We might want to know the mean blood pressure in a certain group of individuals. We might want to know mean body temperature. Some data we'll look at on that maybe Wednesday. Other kind of things we might want to know about a population. Help me out here. We got percentages, that's binomial stuff. We got means, that's usually normal stuff. Any other kind of measurements we've done, like starting in chapter 3?
Incomes,
Different incomes. Okay, so that incomes, we could do mean, we could do proportion, like what proportion of the US population is considered poverty or below. Okay. Do women have a higher mean salary than men in certain professions? Probably not, is what the data shows, right? We can look at some of that. What other things have we measured besides means and proportions in this class? Z-scores, okay, that goes along with means. Something else. What? Standard deviation, that talks about the spread, right? Don't we need to know how spread out a population is? If it's tightly compact or really diverse, right? So that's another thing we might try and estimate about a population. Standard deviation. Maybe of test scores. Maybe you're doing something new in a class and you're trying to target higher test scores with a tight spread. You want everybody around the 80% range. So these are 3 different kinds of measurements we can take. What part of a population fits a characteristic? What's the average measurement of something in a population? How spread out is that population from its center? we are going to, in chapter 7 and 8, going to target proportions and means. If we had another term of statistics here, we would get into trying to estimate standard deviations of populations. We're not going to get to that this term. But we're going to focus on proportions and means. Okay? All right, so 7.2 is all about proportions. And then 7.4, we're skipping 7.3, is all about means. And I'll explain why later we're skipping 7.3. So, we just took a sample. N equals 17 students. X equals 10 of them are female. That gives me a parameter called p hat, which is x over n. In this case, 10 over 17. And we said that is about, what, 0.588? That's to my recollection. Good. So this is an estimate of the proportion of females at BMCC. Got the little and settle down and get excited. You feel this is building up to something really exciting? No. That's the proportion of females at BMCC. Okay. So there's a lot of possible different samples we could take. We happen to take this very convenient sample of 17 people. And we could go stand outside a couple of different buildings and each grab 5 people in some random way, and that might give us a better take on it. Are we going to find that each sample of 17 students is a little bit different? Yeah, they're all going to be a little bit different. Okay. When we do an estimation like this number right there is what's called a point estimate. So the 0.588 is our point estimate for P, the actual proportion. So we have to really be careful. We've got to differentiate. P is the actual proportion of females that attend BMCC. Okay. If I only look at the Pendleton campus, can I possibly estimate that for real? No, because we have other campuses. We have people that take this all over the country. So just gathering people physically is not going to work. I would have to have some other means, like data collection through the computers. So P is the actual proportion. P hat is our estimate based on a single sample. Right? So we have an estimate, we have an actual. And we agreed that there's going to be variation in any sample of 17. Okay. One way to do that is what's called a point estimate. Other times, you get what's called an interval estimate. We're going to go for the interval estimate next. So alternative to a point estimate, but related, it's called an interval estimate. Interval estimate. So an interval estimate is where we say that, let's see, I'm just going to make some shit up and then we'll actually calculate it. If I take like 2% away from that 58%, that's going to give me a 56. Mm-hmm. Or 56.8. If I add on 2, I'm going to get 60.8. So I could say, there's a couple ways to say it. P is about 0.588 plus or minus 0.02. So that's, you ever hear a margin of errors when people give statistics online, like especially for polling about elections? That's really big.
Wait, so is it always 0.02?
I just made that up.
Oh, okay.
Yeah, so I meant I'm going to actually calculate a real margin of error. So I just made the 2% margin of error up.
just sounded nice to use an even number. So that would make our interval. So this makes my interval from 56.8% to 60.8%. So with a 2% margin of error, which I decided for no good reason, based on our sample of 17 people having 10 women, I predict that the actual percentage of females at BMCC is somewhere between 56.8 and 60.8. Now, we usually don't know the actual P, so I think P is in here. That's what I'm saying. Am I right? Or am I wrong? I'm wrong. Yeah, BMCC claims the percent is actually 62%, and 62 ain't in that interval. It's not in there. Oh well, I missed this time. Might I take another sample of 17 and actually get an interval that is in there? Yeah, because every sample is going to be a little bit different. So these interval estimates are also called confidence intervals. So confidence interval, aka interval estimate. They mean the same thing. Interval. Okay, so I'm going to make a confidence interval estimate, and I'm just going to give it to you, and you're just going to have to accept it, and then we'll talk more about it. So I'm going to do a little calculation with my Rabbit calculator. I need, let's see, inverse normal, option 3. How confident do we want to be? Well, the most confident you can be if something is 100%. Are we ever going to be able to be 100%? No, we aren't. Okay, so then we have to settle for some lower confidence, like 90 or 95%. Let's do 90%. Okay, so I'm going to go for a 90% confidence interval. So I'm going to type some magic numbers in here. And that's what I want right there. Okay, so write down this number, 1.644.
That's our
Not yet, I'm working on it. This is what I call z sub alpha over 2, and I'll explain that in just a moment. I think that's 1.644. Okay, what's the mean here? Let's see, it's 10.5-ish. We get that by multiplying NP. Okay. And now I also have to take into consideration that I only have 17 people to work with. And that kind of involves the central limit theorem too. So I get this other weird number I'm going to write down, and that's the square root of p hat times q hat over n. And all of that is inside the root. So let's calculate that. Let's see. What's p hat again?
0.588.
Yeah, so we're going with 0.588. Okay, if that's p hat, q hat's going to be 1 minus that. So I think that's going to be 0.412 maybe? Yep. Did I do that right? Yeah. Okay, and then I'm going to have to divide that by n, which is 17 here. And I'm going to put that inside of a square root. Okay, let's see, what is that about? So 0.588 times, hopefully it's correct, 0.412, not times, but divided by, oops, 17. So this is the magic part that I'll try to explain in a minute. Parentheses and enter. 0.1193-ish, 4-ish, something like that. Okay. So next thing I'm going to do is I'm going to multiply these two numbers together. So I'm going to take that answer, and I'm going to multiply it by my inverse normal, which we're calling 1 times 1.644. And so I think I missed a 4 there, but that's okay. I get something that's about 0.19-ish. If I rounded that to 3 places, what would I call it? 0.196. Okay. Now, depending on where you rounded, you might get slightly different answers. Like, is my p hat exactly 0.588? Just double check. 10 over 17. Oops, I missed something there. Look at division. Try it again. No, it goes on for quite a while. And it may even go farther than the calculator shows. So one thing that's going to happen if we're not careful here is we're going to compound rounding error. And sometimes we need a certain amount of decimal places to be accurate. So I'll do this again more carefully and show you how to avoid rounding until the very end. But we're estimating a number of about 0.196 right now. So we took z sub, oops, is pen, z sub alpha over 2, and we multiplied it by this crazy square root, p hat, q hat over n, and we got about 0.196. This is one method of calculating a margin of error. We usually call that capital E. Okay, so this is a formula that we've got to have memorized. And it's related to combining the idea of a z-score with the mean and standard deviation of a binomial distribution. When we throw all that together and do a little algebra on it, we get this crazy formula right here for the margin of error. Yes?
How do you type in the z sub?
Yeah, so I'll do that for real in just a minute. Yeah, so we're going to go for it now. So now what this says, if I want to be 95% confident about the actual percentage of females at BMCC based on my sample of 17, that should be my margin of error. So let me state this over again. A 95% confidence interval, I'm going to call that a CI, for p hat is going to be, our center is our guess, is the 0.588. We've gone to 3 decimal places on that. Now my margin of error is going to be for plus or minus 0.196, is that what it was? So now I need to get my left hand and my right hand on that interval. So like if I was doing a number line, here's my 0.588. What happens if I subtract from that 0.196? What do I get? .392. So that's about right here on my number line. So this distance right here is my 0.196. Now I got to do the same thing on the other side. I'm going to add the 0.196 to the other side. What does that give me?
0.74.
Okay. So what this means is I am 95% confident that the actual proportion of females is between 0.392 and 0.784. I am 95%. Oh shit, no, that's not right.
It's 90.
90, didn't we go with 90? All right, sorry there, John. You said to go 90% confident. This is a 90% confident interval. So I am 90% confident that actual proportion of females is between 39.2%. Right? My mother would like that better than 0.392. And 0.78, oops, shit, 78.4%. That's right. So my mom might be pretty happy with that. She's like, oh, God, Gary, I'm so glad you're 90% confident that the actual number's in this. My stepfather would say, What do you mean 90% confident? What the hell does that mean, Gary? Well, Bob, what it means is that if I did a whole bunch of other samples of 17 people in the same way, about 90% of them would actually have the real sample percentage in there. And about 10% of them would miss it. Right? So a lot of other samples. Like, let's suppose I did 10 other samples. So here is the actual P. We know it's what? 62%. Yeah. So my sample just now, didn't it contain it? 0.62 is in my interval. And then I do another sample of 17, and that one contains it. And I do another one, and that contains it. And I do another one, and that contains it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what this means. So I make my interval estimates for being 90% confidence. And what that means is roughly 9 out of 10 of those intervals I calculate using 17 people will give me an interval which the actual P is right in there, but 10% of them will not. Does it mean there's a 95% chance that P is actually in my interval? No, that's not what it means. So it doesn't mean that there's a 90% chance that the actual population percent is in my interval. It just means 90% of similar intervals will contain it. Slightly different twist on the idea, but it's important. It is super important that you guys read about this in 7.2, because the calculation is not that bad once you get used to the formula. It's pushing a few buttons on the calculator. But what does it mean probabilistically? That's what we got to spend a few days working on. And this is going to cover, this is going to be in chapter 7 and 8. Same ideas are slightly different calculation for each kind of thing that we do. So we're trying to make an interval estimate that grabs some population percentage. In this case, we went for a 90% confidence interval. Now, would you say this interval is kind of wide, 39% to 78%? Yeah. And if we instead said, let's do a 95% confidence interval, that's going to make the interval wider. The more confident you want to be, you have to widen what you'll accept for the population proportion. If you want a narrower interval to contain that number, then you're just going to have to accept being less confident. So we'd have to jump down to 80% or 70% if we wanted a smaller interval, which means we have a higher chance of creating intervals that miss it, the actual number. And the problem is we usually don't know the actual number, so that's one reason repeated small samples are popular. Question, John?
So the formula is that you had that's all that you do.
Yeah, so let me write this down, and then we'll actually apply it to another example. All right, so confidence intervals for population mean, population proportions. Intervals. And this is section 7.2 for proportions, aka percents. What percent of the population is female? What percent of the population is African American? What percent of the population are math teachers? That's the kind of thing I'm talking about right here. And the confidence interval looks like this. We have our number p hat that we calculate, and then we add or subtract our margin of error from that. And the margin of error is always a special z-score that's referred to as z sub alpha over 2. And I'll diagram what that means in a sec. Times the square root of p hat q hat over n. And that n is in the square root also. Can you get that from the way I drew it?
And define p hat again, what is it?
P hat is x over n. So what the hell is z sub alpha over 2? It is like a percentile. So I'll explain where that percentile comes from. So let's go for a new page for that. These are called critical values. Critical values. In particular, we're looking, sometimes they're called z sub alpha. We're going to call ours alpha over 2. You'll see why. So I'm going to draw a normal distribution because we were looking at the idea of approximating a binomial with a normal. And I'm going to use z-scores. So what's the mean for a z-score? 0, correct. Earlier, I asked John, or I asked the class, and John picked, how confident do we want to be of our interval estimate? And we went for 90%. So the 90% is what goes in the middle here. And the 90% is what's referred to as a confidence level. What level of confidence do you have in the calculation you just did? We went for a 90% confidence level. Okay, and I'll keep explaining as we do these problems what the hell that means after we calculate it. Confidence level, I usually abbreviate CL for confidence level. That's the 90. Well, if there's 90 in the middle, what's there outside of that? 10%, right? So if we take 1 minus the confidence level, that gives me what the tails have to share. That's what's called alpha. So in this case, 1 minus 0.9 equals 0.1, or 10%. That is my alpha in this case. Each tail gets to split alpha, because I'm trying to center my confidence interval on the mean, or my proportion in this case, p hat. So let's see, to do that, I'm going to have to take my 10% and divide it by 2. So that's going to give me 5% in each tail. And again, this area over here is what we call alpha over 2, which in this case is 5%. Now, what I want to do is I want to know what z-score is this. Z-score. Which tool on the calculator do I use to figure out z-scores given a percentage? Inverse normal. Yeah, I need to do an inverse normal. Now, how does the inverse normal work? Does it work on intervals, left tails, or right tails? It only works on left tails. So that means to find out this z-score, I need to know what is in the left tail. What's the percentage in this particular left tail? It's going to be my confidence level plus that alpha over 2 in the other tail, which is 90% plus 5%. So do you guys agree my left tail has 95% in it? So once we're given a confidence level, we need to know alpha. Then we need to add that, split that alpha, and add one of them on so I can make the left tail complete. So now to figure out the z-score, I'm going to enter the inverse norm for, in this case, 95%. Right? Is 95% my confidence level? No, it's the confidence level plus the left tail. Okay? To get the right z-score, I got to be careful about that. And then I'm doing z-scores, so it's a 0, 1. What do you get when you do that? Inverse normal of 95%. So 0.95. 1.644, like I was using, right? Yeah, so that number I didn't just make up. I calculated it. So 1.64 is the approximate z-score for a 95% confidence level, which puts 5% in each tail. So you know all the pictures we were drawing of normal distributions in the last chapter? They're super important now because they help me sort out what to do. All right, so let's try this on a different problem. So I got a few other problems to play with. Let's see which one looks cute. Is the height? Oh, here's a good one. The MCC also claims that 38% of students here are over 25 years old. Can I count as a student since I took yoga in the winter?
Sure.
Thank you. Good. Okay, so there's 18 of us here. Let's do this. Okay, so claim. Now, often we don't have a claim. We just go right for the data. Okay, and we're trying to make a claim ourselves. Okay, so we're just going to go with BMCC's claim, and we're going to test it with a confidence interval. So the claim is that 38% of BMCC students are over 25 years of age. Are over 25 years of age. So I don't need to know your exact age. I just need to know if you're over 25 years of age. All right, so raise your hand if you are over 25 years old. 1, 2, 3, 4, 5, 6, 7. Is that right? There's 7 of us? Okay. So we have x equals 7 out of n equals 18. 7 out of 18. All right. So let's calculate p hat. P hat is exactly 7 out of 18. So that means I know q hat has to be what, 11 out of 18 then? Because that means if there's 18 total, 11 must be 25 or under. Okay. What is this approximately 7/18ths? 0.389? Cool. That's kind of close, huh? And so that makes q hat approximately 0.611?
Yes.
So about 38.9% of the people in this room are over 25 years of age, and so about 61.1% of us are 25 years or younger. All right, next. What is our estimate of the proportion of people over the age of 25 at the MCC? What is it? It's our 30. Well, ours is 38.9. Right? That's our estimate. That's called a point estimate. So p hat, which is approximately 38.9%, is our what's called a point estimate for the percent of over 25-year-olds. Now, caution, this is not a random sample, so it's a little bit dangerous, but looks pretty good, isn't it? Okay, now what we're going to do is we're going to calculate a margin of error for a given percent confidence. So how confident do we want to be, Melissa? In because we're going to put a margin of error. We're going to say it's 38.9% plus or minus blah, blah, blah. But we need to establish a confidence level first.
That's pretty good. Okay.
90, Melissa, sorry. What's the probability I'll get your name right? No, I keep doing that. So Melissa and I said, let's go for a 95% confidence interval. So that means our confidence level, and I recommend when you're figuring out confidence levels, you draw a picture of it. So we're going to go for a confidence level of 95%. What's alpha then? 5%, yeah. And what is alpha over 2? It'd be 2.5%, which as a decimal would be 0.025, correct? Move the decimal place twice to the left. Okay, so I'm just going to draw a cute little picture of this. I'm going for 95% in the middle. That's going to be my interval, and I need to figure out what are these z values. Well, since the center is 0, they're symmetric. If I figure out the number on the right, the number on the left is the opposite of that. So sometimes it's easier to go for the number on the left, right? So check this out. What percent is in my left tail only?
2.5.
Yeah, this is 2.5 or 0.025. So I could identify this z-score by saying, give me the inverse normal, or inverse norm, of 0.025, comma 0, comma 1. I'll do both calculations just to confirm this is legitimate.
So does it matter if you change the decimal to a percent and the inverse?
So I like using percentages when I'm talking to people, but the calculator expects it to be a decimal, right? So inverse norm option 3, 0.025, 0.1 paste, and I get a negative 1.9599-ish, often abbreviated negative 1.96. Okay. I'm also going to do a full left tail, and so that would be 95% plus the left tail, which gives me altogether 97.5. So if I repeat the inverse normal with 97.5, I should get the positive version of that number. So where the hell am I getting the 97.5? Calculate it and I'll remind you. Notice the similarity in those two numbers? Right? They're just opposite each other. So what I did again was I said I want to find this z-score, and inverse normal needs this whole tail, which would be the 95% plus the 2.5%. So I had to do the inverse normal on 0.975, 0, 1. And these numbers are just going to be opposites of each other. So whichever one is easy to do for you, you do that one. Okay. But when it comes down to stating my margin of error, I'm going to use the positive version. It doesn't matter which way I calculate. So to 2 decimal places, what's my z-score? 1.96 is what we're going to go with. Okay. Cool. So now we're going to calculate the margin of error. That's called E, and E is always the critical z-score, which for us is called z sub alpha over 2. That's called the critical score, times this little fudge factor, p hat times q hat over n in the square root. Okay, so for us, it's going to be approximately, because I've already rounded, 1.96 times my square root. And inside my square root is p. I'm going to use the fraction versions, if that's okay. My fraction version was what, 7 out of 18? So I could just go here and do 7/18 times, what's the other fraction that I'd use then? 11 out of 18. So I can just keep going. 11/18. And then I have to divide finally by n, which is 18. So if you type that in your calculator, that's going to, order of operation there is just fine. The calculator will love it. Let's find out what our margin of error is for a 95% confidence interval. And again, the bigger our confidence level, the wider the interval is going to be. We have a little bit of control over that, and I'll explain why next. So what do I have? I have 7 over 18 times 11 over, oops, I missed something. What's the times of that? 11 over 18 divided by 18? About 0.225 is our margin of error here. So we think that the proportion of people at BMCC that are over 25 is about 38.9% with a margin of error of 22.5%. Holy shit, that's a big margin of error. Don't like in polls you hear with a margin of error of like 1 or 2%. We get a margin of error of 22.5%. But hey, we are 95% confident the actual percentage of over 25-year-olds is in there. So how many people would like to have a tighter margin of error, or a smaller margin of error? I would too. Okay, so we don't have much control over that in the moment with the sample we got, besides lowering our confidence level. Right, so I'm going to go for a 50% confidence level. I'm going to go 50% confident. That's not very confident, is it? That's pretty wishy-washy, right? Yeah. But it's going to make my margin of error smaller. So I'm just going to do that quick and see what I get. So if I go for a 50% confidence interval, that means that my my tails will have half of 50%, or 25% in them. It's a pig tail. So that means my z-score would be negative or positive 6.7-ish. So next I'm going to take that and I'm going to multiply it by that crazy square root I just had and see what our margin of error is going to be. So 7 over 18 times 11 over 18. So did you see how by using fractions I didn't have to worry about rounding there? That's one way to minimize rounding error. You just got to be careful when you type it. Hey, that's better. Now, it made it negative, but it really should be positive. So now I have like a 7.8% margin of error. Better than 22.5% margin of error, agreed? But wouldn't it be nice to be able to have like a less than 5% margin of error? Okay, so clearly the problem is my sample. That's the only other thing I can change here. Okay, so what's wrong with, there's two things wrong with my sample. Can anybody tell me what they are? There's not enough people is the big thing, and it's like, although my 38% is pretty nice, it's not random. Right? So usually we want a random sample, and I made no effort to get a random sample. I just said, you guys are so convenient, I'm going to use you. So really I want to control n. And I can do that. So let's now what we're going to do is we're going to estimate a better sample size. Because I think 18 is too small. Better sample size. Okay, so what do we have to work with to do this? So let's write down, so it's the margin of error we're fiddling with. And margin of error is equal to your z sub alpha over 2. And the z-score depends on your confidence level. Okay, so we have some control over that. Lower the confidence level, that lowers the interval too. Okay, times the square root of p hat q hat. I don't have control over p hat and q hat. They are what they are when you take the data. But I do have control over how many people I ask, how many people I survey. So what we're going to do for simplicity, we're going to go with a confidence level of 90%. Well, let's see. Well, we had 95% before. I guess I better stick with that. Let's go with the 95% confidence level. So what's my z-score going to be for a 95% confidence level? 1.96. Yeah, so that means z 0.025 is going to be about equal to 1.96. Okay, so that simplifies my formula a bit. I have 1.96 about there. All right. Ooh, now here's a little problem. I don't have a sample yet, kind of, or maybe I do. In some circumstances, you want to know how many people to survey, but you don't know what p hat and q hat are yet. You have two choices there. One, make a wild guess, or go for 0.5. Those are your choices. Could we make a wild guess here? Yeah, we got this sample of 17 to make a wild guess. It's not totally wild. We narrowed it down a little bit. If you thought that sample was totally bogus, then you would just go with 0.5 for p hat. So what do you think? Should we go with this sample or should we go with the 0.5? Is this sample bogus? Given that we know BMCC thinks there's 38%, and this class came out to 38.9%, I say we go with that. Yeah. So we're going to go with p hat is 11/18. Oh no, shit, hold on. 7/18. The other one is 11/18. I almost did it again. That's supposed to be a 7 times 11/18. And then what we're going to do is we're going to try and solve this for n. Oh, wait, there's something missing. What's on the other side?
0?
No?
1.9.
No? What's e? It's our margin of error. Yeah, to estimate a sample size, you get to choose your margin of error. Pretty cool. What do we want our margin of error to be? 0. No, we can't do that. That makes it impossible to solve. We got to pick something like 5%, 2%, 1%, or
1%.
1%, 5%. Let's go with 1%. We're going to go for a margin of error of 1%. As a decimal, that would be 0.01, right? 1%. Equal sign. So what that means is we have to attempt to solve this equation. Okay. So I'll just help you out with that. It's not as bad as it looks. No, it's not. Okay, so we're going with 1%. I'm going to write it as 1% for a moment, right? On the other side, I'm just going to call that z. And then for, this is p hat, that's q hat. And there's n down there. So to solve this equation for n, I first need to remove the z, right? You get away with things outside first. So that means I'm going to have to take my 1% and divide it by z. Right? I want to divide, because z is multiplied on this side. I want to break that bond of multiplication by dividing. Okay, so that gives me on the other side the square root. How do I get rid of square roots?
Square.
Yeah, square both sides. Okay, so then I'm going to take what I want my margin of error to be over z, and I'm going to square that sucker. Now I have p hat, q hat, over n. All right, who's good at algebra here? What else could I do here? I'm trying to get n alone.
Times it.
I could multiply n over, yeah. I could definitely do that. That would give me, if I multiply everything by n, that would give me n times this squared parentheses equals p hat times q hat. Hey, we're almost there. What's the last thing to do?
Divide by the.
Divide by that crazy squared thing, yeah. Divide by the crazy squared thing. So I'm going to do that next. See if my magic pen can do it for me. Yes. So I'm just going to divide by that. Oh, cheater. Cheater, I know. There, I divided by that. So now I have an estimate for n. Okay, so what does it say? To estimate n, you take p hat times q hat, and then you divide by the square of your new margin of error divided by your critical z-score. We can do that. Let's do it. So I'm going to write down what that means for us. So for us, n is going to be, let's see, p hat was 7/18. So let me write it in calculator notation. So that's going to be 7/18 times q hat, which is 11/18, right? Oops. Calculator way. It's going to give me 11/18. And then the formula says to divide, okay, by parentheses. What's my margin of error here going to be? We're aiming for 1%. Okay. So 0.01 over the z-score, which is 1.96. Close the parentheses and square it. Okay, let's pray we all come up with the same number. Let's whip that sucker out. There's a different way to write this formula, which we'll look at later. Let's get a calculation. So, 7/18 times 11/18, that's the easy part, divided by parentheses, because the denominator is complicated, 1.96, no, I'll get that backwards, 0.01 divided by 1.96. 0.01 divided by 1.96, close the denominator parentheses, and then square it. Enter. I get that I should have a sample size of 9,130 if I want my margin of error to be 1%.
Oh, no.
Are we going to go for a margin of error of 1%?
No.
Nah, I don't think so. Let's try 5%. All right, now that's easy. All I have to do is go back to my formula and replace the 1% with a 5%. So now once I have that formula in there, I can just tweak it until I get something that makes me happy. Welcome to the world of statistics. You get to pick the way things turn out, kind of. 5%, hey, that's not so bad. I only have to interview 365 people. That's better than 9,000, ain't it?
It's like,
It's like a lot, right? It's not as nice as 17. Okay. So you have to make a decision. Can you live with a 5% margin of error? If so, then you have to survey at least 366 people. If you want a smaller margin, if you want to aim for a smaller margin of error, then guess what? You got to survey more people. Yeah. So it's a combination of playing around with how confident you want to be, Melissa, 95, 90, and then what you can handle for a margin of error and how many people you can afford to survey. And all those things go together to make a prediction about something going on. Pretty cool, huh? That's exciting. Okay, so on Wednesday, we will do a couple more problems in 7.2. The 7.2 homework is up. And time permitting, we will start 7.3. We'll see how it goes.